Hey everybody, welcome back to the Feynman Technique. It's been a while since I've posted two videos in one day, but the integral I solved in my last video was not that interesting. It's a standard integral result, but it laid the foundation for the technique that I'm going to be using in my next several videos. Again, these will not have Feynman integration in them. As I explained in my last video, I'm having a little trouble coming up with new original integrals to solve using Feynman integration that aren't just basically reparameterization or, old videos with, just different constant values or just very similar to old videos. So taking a break and now we're going to solve some integrals using this other technique. Um, so the integrals we're going to be solving today are these integrals. And these are technically solvable using standard calculus techniques like integration by parts, partial fractions, and all that good stuff. I would not recommend attempting these videos using those techniques, though. Instead, we're going to follow pretty much an identical process uh, to the method I employed in my last video. And in my last video, I started with a standard result. So that's what I'm going to do in this video. We're going to start with this standard result. And if this is not standard, if you don't consider that standard, I can show you how it's derived. I'll link to my previous video in the description of this video. But anyway, we're going to start with this result. That is the integral from 0 to infinity of 1 over x to the fourth plus 1 dx is pi square root of 2 over 4. All right. Now we're going to reparameterize that integral. We're just going to replace that 1 with an a to the fourth. And then we're going to factor out that a to the fourth like this. So these two integrals are the same. Next, we're going to make the substitution u is equal to x over a, just like we did in the last video. Therefore, dx is equal to a du. Applying that substitution will give us this, that the integral from 0 to infinity of 1 over x to the fourth plus a to the fourth is equal to pi square root of 2 over 4a cubed. All right, what now? Well, let's let our a equal I to the 1/4. Now, the principal value of I is e to the I pi over 2. Raising that to the 1/4 will give us e to the I pi over 8. All right, so we're plugging in e to the I pi over 8, or just I to the 1/4, the fourth root of I, into this equality. All right, so what we get is that the integral from 0 to infinity of 1 over x to the fourth plus I, notice that we plug in a is equal to I to the 1/4 and then raise it to the fourth power. That's just going to give us I. And then substituting e to the I pi over 8 into this, that gives us this. And then we can multiply the top and the bottom of the integrand of this integral by x to the fourth minus I, giving us this, which just gives us this. Because if we FOIL this out, we'll just get x to the fourth, x to the eighth minus I squared, which is just plus 1. All right, so now we have this. We have that the integral from 0 to infinity is equal to the integral from 0 to infinity of x to the fourth plus I is equal to the integral from 0 to infinity of x to the fourth minus I over x to the eighth plus 1 dx. And now this form right here, you can kind of make a connection to our original integrals up there. So now, we just restate this basically, that this integral right here is equal to this. And using Euler's formula, we can break up e to the negative 3i pi over 8 into its cosine and sine parts, like this. Euler's formula, of course, says that e to the I theta is equal to cosine theta minus I sine theta. Cosine of negative theta is just cosine theta, and sine negative theta is negative sine theta. So that's how we get here. All right. Now, cosine of 3 pi over 8 and sine 3 pi over 8 are not standard trig results, but you can use the half angle identities to derive both of those. And this is what you get. Cosine 3 pi over 8 is the square root of 2 minus square root of 2 all over 2. And sine 3 pi over 8 is equal to the square root of 2 plus square root of 2 over 2. Okay, so plugging that back in, and we get this. The integral from 0 to infinity of x to the 4th minus I over x to the 8th plus 1 is equal to this right here. And now we're done. We literally just match up the real and imaginary parts of this result, and we have the answers to our original integrals. So coming up with those solutions using standard integration techniques would be extremely, extremely time consuming. And you can see we got to the answers pretty quickly here. So anyway, guys, we're going to continue using this technique in future videos. You could see we could, using this result now, you can see we could easily come up with the answer to the integral from 0 to infinity of both 1 over x to the 16th plus 1 and x to the 8th over x to the 16th plus 1 using this same iterative process. So I hope you guys enjoyed that, and we will see you next time.